Hi everybody, it's Mrs. Harbin. We're doing video notes 8.1 stoichiometry. Got a little Bruno Mars in the background just because you'll see in a second. So here's what we're doing. And we're going to be doing lots of problems with this, so make sure you know your mole stuff. It'll be helpful. Make sure to look at chapter 9. It's really fine. That rhymes. I know. These sections you need to read. Now here, put this problem into your notes after you do this PowerPoint, okay? Make sure to look at the example 9.5 in order to understand it. Okay, so here we go. Yeah, those are the book connections, and here we go with the real world connections. Thank you, Bruno Mars. Yeah, over and out. So, stoichiometry, it's the mathematics of chemical equations. So, because chemists do chemical reactions, we want to know, well, what if we start with 50 grams of salt and 3 crackers? How many Cheez-Its are we going to get? That mouse wants to know too. So, stoichiometry needs a few things. You need to have a balanced chemical equation. You need to be given an amount of grams, liters, or molecules. Atoms are formula units. Grams, liters, are tiny pieces. And what you want to find, of course. What you want to find. So, hey, if we were making tricycles for this here bear, there might be a formula for it. 3 wheels, 1 frame, and come together to make 1 tricycle. Assuming we had an infinite number of frames available, how many tricycles can Sammy make with 9 wheels? Well, let's see. If we start with 9 wheels, we can multiply by a ratio saying that based on this, every 3 wheels will give us 1 tricycle. So 9 times 1 divided by 3, wheels cancel out. We're left with tricycles. 9 divided by 3 is 3 tricycles. So with 9 wheels, we'll make 3 tricycles as long as we have enough frames to do it. So what we're working on here is the ratio of things in a balanced equation. Okay, and we had to know what those things are. So those things are moles. Okay, moles. Moles are relating a balanced equation by coefficients. Because we could say I have 2 formula units of that, and I make 2 formula units of that and 3 molecules of that. Those are so stinking small that we'd probably want to get a whole bunch. So coefficients are moles. Coefficients are moles. Coefficients are moles. Make sure you know that. Are moles. So what are coefficients? They're moles. Moles of what? Moles of everything behind it, of each thing behind it. So, now, I can change one kind of mole into another kind as long as I have a balanced equation with coefficients. So if we have 12.3 grams of KClO3, look, unit identity, we want to react it to see how much O2 is going to form. We have to change KClO3 into O2. We need a balanced equation, but these are moles, so we're given grams of potassium chlorate. We need to change that. So we go get the periodic table and we add up potassium plus chlorine plus 3 oxygen, we get 122.55 grams of KClO3 for every 1 mole of KClO3. Now that we have moles, we can use this mole ratio coefficients to change KClO3 into O2 because that's what we want to find. All right, but we're in moles. We have to be in moles to use these because coefficients are moles. I look to see what's in front of the KClO3 and it's a coefficient of 2. In front of the oxygen is a coefficient of 3. We're not done yet because we want grams of oxygen, so I want grams of oxygen. So I got to change these moles of oxygen into grams. 1 mole of oxygen is 32.00 grams from the periodic table. And then I do the math for that and I get 12.3 divided by 122.55 times 3 divided by 2 times 32 gives us 4.82 grams of oxygen. All right, so what does this mean, you say? It means if I start with 12.3 grams of this, I should be able to get 4.82 grams of that out of that chemical reaction. And that's the math of chemistry. Stoichiometry, woo. Okay, here's that same equation again. This time we're only using 4.53 grams of potassium chlorate. So given, what are we trying to find? Liters of oxygen. Okay, so this time we don't want grams, we want liters, and we want to change the identity of this into identity of that. You can only change identity at the mole ratio step. So you change grams of potassium chlorate into moles of potassium chlorate. And now that we have moles of potassium chlorate from the previous step, we can cancel that out. But here's where we change identity. And again, we're looking for oxygen because that's what the question asks. We could have been looking for KCl. That'd be fine too. All right, where do I get the numbers to put in a mole-to-mole ratio? Mole ratios of one identity to another come from the balanced equation, coefficients, 2 and a 3. All right, don't forget to get the coefficients for the mole ratios of two substances. That's why they need an identity. This time, though, back to 1 mole equals 22.4 liters at STP of oxygen. Calculator time. Let's go, let's go. All right. Hey, I want you to calculate that and then see what you get, and we'll talk in class, okay? So I can make sure you're doing your math right. But that's how you set it up. Look, bye-bye potassium chlorate. See you later, moles of potassium chlorate. Bye-bye moles of oxygen. Hello, liters of oxygen. We converted the identity of this into the identity of that using the connection of the mole ratio coefficients. Okay, another balanced equation. Woo! This time we're starting with molecules. 5.67 times 10 to the 23rd molecules of oxygen. All right, what am I trying to find? Find liters of carbon dioxide. So I want to change oxygen into carbon dioxide. So I only need to worry about those two things in my balanced equation. Molecules of oxygen have to change to moles because the only place where you can change identity is at the mole ratio. Moles of oxygen have to turn into moles of carbon dioxide. This time, though, I want to change it to liters. Moles of carbon dioxide. I changed its identity. We need some numbers. Yeah, some number. Moles are number 1 when it's moles and molecules. Avogadro's number for molecules. Hey, it's moles of one kind and moles of another. Where do I go get where do I get those numbers? Moles to moles coefficients. So a 2 for carbon dioxide and a hey, there's nothing there. You're right, it's a 1. It's a coefficient of 1, so there is something there. And then this is back to the definition of moles. 1 mole equals 22.4 liters because this is carbon dioxide and so is that. So molecules of oxygen cancel. Moles of oxygen cancel. Moles of carbon dioxide cancel. And you plug it in. 5.67 second E 23 divided by 6.02 second E 23 times 2 times 22.4. I get 42.2 liters of carbon dioxide can form in that reaction. So if this many molecules goes in, that many liters should come out. Okay, another reaction. Now here's the part we didn't talk about is that you do need a balanced equation. So for this one, I'm writing it for you, but I'm canceling charge for all the compounds. Barium's got a +2, nitrate's got a -1. All right, then I need coefficients. I have 2, I need 2 nitrates, I need 2 chlorides, 2 silvers. So there we go. You might have to still be able to do this. Lucky we practiced. Okay, so I've got 15.8, so that's my given, 15.8 grams of silver nitrate, and I want to change it into grams of silver chloride. So I have my balanced equation, grams of silver nitrate, have to change into moles of silver nitrate, because then I could change moles of one kind, moles of silver nitrate. Hey, I'm at North. Did you hear that bell? Change it into moles of silver chloride. Okay, but I'm not done because I want grams of. Sorry. Hey, who said that? All right, so moles of silver chloride change into grams of silver chloride. Okay. Stop and look what I just did here. Look at grams of silver nitrate cancel, moles cancel. Here's the point where I change the identity. Moles to moles. What goes in a mole to mole ratio? Coefficient. So I find the silver nitrate has a 2. I'm sorry, silver chloride has a 2. Silver nitrate has a 2. Leave them as the coefficients. Over here, it's a definition of a mole. 1 mole equals, and I got to go get silver nitrate from the periodic table. Silver 107.87 plus nitrogen plus 3 oxygens, get 169.88. Over on this side, 1 mole equals, and now I got to do silver plus chloride over here, plus silver plus chloride, and I get 143.32. Okay, and then you do the math. See a grams of silver nitrate, bye-bye moles of silver nitrate. Hello, moles of silver chloride. You're going away. Bye-bye. So now we have grams of silver chloride. Woo, silver chloride is precipitating. What? Precipitating. Put a solid there. Yay. 15.8 divided by 169.88 Times 2 divided by 2 is 1. So times 143.32, enter. Looks to me like I'm going to get 13.3 grams of silver chloride. Basically, if this many grams of this go into this chemical reaction, then this many grams of silver chloride should come out. That's if everything's perfect. We'll find out what that means later. Okay, hey, here's what I want you to remember. Coefficient ratios work for balanced equations as long as you're using the coefficients as moles, okay? So I could do any kind of mole ratio from this. I could say 2 mole KCl for every 3 mole O2. I can also say 3 mole O2 for every 2 mole KClO3. So you can compare any two things in the balanced equation. I could also flip those over. I could use KCl and KClO3. So you can use those coefficients as moles. You can also use them as tiny pieces, atoms, molecules, or formula units. This would be a formula unit. I'll do it the nice way for you. Another for you. And this one's a molecule. All right. Because a balanced equation talks about the tiny pieces of chemistry or a bunch of those tiny pieces together. So moles, atoms, molecules, formula units. Please never use the coefficients as grams. Okay, so, oops, I shouldn't cross that out. Read that. But you can never say 2 grams of KClO3 for every 3 grams of O2. That is so wrong. Wronger than wrong could be. No, 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 no. They are not grams. Coefficients are not grams. Okay. So review. Always go through moles. Moles. Hey, Bruno's back. Moles over moles use coefficients. You can change reactants to products. You can change reactants to other reactants or products to other reactants, and back and forth anywhere in a balanced equation using mole ratios. All right. Be sure to read your book. Now go back and do this. If you want to know what a conversion string is, I'll tell you that your book, I'm going back here, does each step separate, separate, separate. This is a conversion string when you do all of the conversions right in a row. Okay? So go for it, do it. Peace out. Thanks, Bruno, for helping us with this PowerPoint.